Arithmetic sequence. A sequence where each term differs by a constant arithmetically. In this sequence, the sequence begins with a 3 and differs by 2 from one term to the next. Let's say we want to find the fifth term of this sequence. Then one will have to add 3, the first term, and 2, the difference, multiplied by 4, because there are 4 2's. The result is 11, which is the fifth term of this sequence. Then, in the general case, to find the nth term of any arithmetic sequence, an, one would have to add the first term, a1, with the difference, b, multiplied by n minus 1, the amount of b separating a1 from an. Next, arithmetic sequence sum. That is to say the sum from the first term to the nth term of an arithmetic sequence. Let's say that we want to know the sum of this sequence from the first term to the fifth term. All you have to do is add up the terms manually. Easy. The result is 35. But what if we want to know the sum of this sequence to the hundredth place? It will take too long to calculate manually. Yes, it's easy to use a calculator, but that's besides the point. Let's do this with another example. A sequence where it starts with the number 1 and each terms are separated by 1. The sum to the hundredth place should be this. It is known that if we duplicate this sequence, flip it, and add them up, you'll get the same number added repeatedly. In this case, that number is 101, added 100 times. The result of two of the sum added together is 10,100. Therefore, the sum on its own should be the result divided by 2, which is 5050. The same applies to our original sequence. Duplicate, flip, add, and divide. We can apply this technique to get the general form of the sum of any arithmetic sequence to the nth term. Duplicate, flip, add, and divide. Those are what most people know, but there's more. A quadratic arithmetic sequence, or as I would like to call it, a second-order arithmetic sequence, is an arithmetic sequence where every term differs by a first-order arithmetic sequence. In this case, the nth term is equal to n squared, and, as visualized, is separated by a first-order arithmetic sequence. We already know the formula to this sequence, but what about we try to find the sixth term of this sequence through another perspective? The sixth term should be the result of, similar to the first-order arithmetic sequence, the addition of the first term, 1, and the terms below it until the fifth term, 3, 5, 7, 9, and 11. The result is 36, of course. But what's interesting is that we were adding the first term with the sum of the lower sequence to the fifth place. So, to generalize this, the nth term of this sequence is equal to the addition of the first term and the sum of the first order arithmetic sequence to the n minus 1th place. Then, what is this equal to? Recall that we already know the first order arithmetic sequence sum. So, just substitute that in and we get this as our answer. So, these are all we have so far. But what about the sum of the second order arithmetic sequence? Also note how the second order arithmetic sequence formula contains the first order arithmetic sequence formula inside of it. So, what's the sum of our sequence? Well, since our second order arithmetic sequence formula contains the first order arithmetic sequence formula, the first two terms are already taken care of. The problem now gets reduced to only the last term. But we can't use the duplicate, flip, add, divide trick on it. It's too complicated, so I did this instead. If you rewrite the second order arithmetic sequence formula as a trinomial and instead of x, you'll get this. Then the sum of the second order arithmetic sequence should also have the same coefficient as the formula, since it's just the same formula with different n values added together. Now we can work this through individual terms. The constant is always the same no matter what, so the sum would just be it times n. We can use the duplicate, flip, add, divide trick on the second term. The only thing left is the third term. The problem is now easier to solve, since the only thing we need to do is to find what to substitute n squared with instead of whatever it was before. We can set a1, b1, and c to only leave us with n squared as the formula. So all we have to do now is to find the general formula for the sum of squares of the first n natural numbers, which can be visualized as this. Every layer represents its respective layer number squared. The topmost layer has 1 cube, second layer has 4 cubes, third layer has 9 cubes, and so on. Pretend for now that this visualization is n wide, n long, and n high. We then triplicate the structure and put them together like this, and duplicate it, although the other structure is a mirrored version of the original, and stack them on top of each other. The resulting is a giant block with side lengths of n plus 1, and 2 times n plus 1. And since this giant block is equal to 6th of our structure, the sum of squares of the first n natural numbers is this, which is what we will put in as our last term. So, this is the second order arithmetic sequence sum formula. And this is the same formula reverted back to its original form, or at least my choice of form. Let's cut to the chase. The third order arithmetic sequence formula will just be the first term plus the sum of the lower sequence to the n minus 1th term. So just substitute the sum with the formula we already know, and we have the third order arithmetic sequence formula. But what about the sum though? Well, everything is set except for the fourth term, since we can't use the duplicate, flip, add, divide trick or geometry visualization on it, since that would require us to visualize it in the fourth dimension. So there's nothing we can do. Let's return to the formulas. Returning back to this, there seems to be a pattern. For every increment of the arithmetic sequence order, the only thing different about the formula is the new term that gets added. The term seems to follow a pattern. The numerator gets multiplied by a further decrease of n, and the denominator seems to be a factorial. And the fact that the number of terms in the numerator is equal to the number being factorial in the denominator means that these are binomial coefficients. If we follow the pattern, the third order arithmetic sequence sum formula should be this. Let's use it on a random arithmetic sequence. Here are a1 equal to 4, b1 equal to 7, c1 equal to 2, and d equal to 5. The sum of this sequence until, let's say, the sixth term is 4 plus 11 plus 20 plus 36 plus 64 plus 109, which is equal to 244. Now, let's try calculating it using our formula. Seems like it works, which means we can graph out the fourth order arithmetic sequence formula as well, which also follows the pattern that we found. So, the general formula for nth order arithmetic sequence and its sum are just the first term of each layer multiplied by a binomial coefficient added together. In other words, this, where big N corresponds to the arithmetic sequence order, T corresponds to the first term of each layer nominated by I starting from the top, and N corresponds to which term in the sequence you want to calculate or calculate to. So that's it, and thanks for watching.